minus 3. The value is 0.733. Okay. So now we go back up. What we have? We have 0.8, 0.6. We don't have 0.733. So 0.733 is somewhere in between. Okay. So this is an approximation. Okay. So you just 0.733, you just eyeball it. Okay. You just eyeball this 0.733. Okay, so this is 0.6, 0.8, 0.733 is somewhere around here. So why I put somewhere around there, okay, is I'm going to sketch a line. I'm going to sketch a line which is green. Okay, so I'm going to sketch. Okay, so this is your 0.733 line. Okay, so approximately, you see, okay, so approximately this is about 90. Okay, so if this question were to come out, you just need to, I will follow your numbers. Okay, but you have to show me how you determine the numbers. You have to write down that this is your 109.2. Over here is your 90. Okay, so we know that from the chart, PCR over A. Okay, so from the chart, okay, PCR over A is equal to 90 times 10 to the power 6 Pascal. Okay, so from here, we calculate our critical load will be equal to 90 times 10 to the power 6 multiplied by your area, which is 5700 times 10 to the power minus 6. So 90 power 6 times by 5700 power minus 6. Wait. 90 power 6 times by 5700 power minus 6 is equal to 513 times 10 to the power 3 Newton. Okay. So we know the calculation for factor of safety is equal to P critical divided by P. So this is 513 times 10 to the power 3 divided by the applied load P, which is equal to 175 times 10 to the power 3. So 513 power 3 divided by 175 power 3 is equal to 2.93. So what you can see over here with the chart, right? With this chart, which I show you how to use, the calculation is much more what? Simpler, yes or no? Relative to the previous example. The previous example, can you all imagine how many steps you have to take? Okay. Right. So that is for eccentric loading. Okay. So the last part of buckling, okay, that we're going to do.
I have a few questions.
Okay. Yes.
Why the radius of gyration is about the z-axis?
Because 6.95 is lower than 70.8. So you have to use 34.8 as the radius of gyration.
Okay, and could you re-explain why the both ends are pink?
Because over here, the force applied below here is just one force applied. There's no moment, right? So M
Yep.
equals 0. At the top, there's only one force applied. There's no resistant moment. So M is also equal to 0. So when moment is equal to 0, like over here, moment is equal to 0, moment is equal to 0, that's why it's pin.
Yeah, but how do you know the moment is 0?
Because it's pinned. There's only one point touching at the bottom at the top. Okay, if I were to remove this force, the top force, the entire structure will rotate downwards, yes or no? It's not built
No.
in. It's not built in, right?
Yeah.
Yeah, that's why it's pinned. So if you look at the built in, right? If you look at the previous example, it is built in. Can you see this?
Yeah.
It's different, yes or no? What
Yeah.
we have on the other one is just a single point pin. So there's no resisting moment. So to see whether what sort of holding system you have to watch your moment.
Okay.
Okay, you have to watch your moment. That's the way to see how the structure is fixture.
Yeah. Thank you.
Okay. Anyone, any question? Tony.
Yeah, can you go over how you use the chart again?
Okay. So how I use the chart, you have, so if you look at the chart, you have to see what is on the chart. Is on the x-axis is LE over R, right? On come on. On the x-axis is LE over R. The y-axis is P over A, and all this individual red line is EC over R squared. So you have to calculate your LE over R first, and then also calculate your EC over R. Then our EC over R is 0.733, right? So I just sketch this line over here. This is just a sketch. Okay, I just sketch. Then from here, you read the value of P over A is equal to 90 times 10 to the power 6 Pascal.
Okay, makes sense. Thank you.
Okay. Anyone else any question? You can see with this chart the calculation is much more simpler. Okay, your calculation is much more simple. But again, you have to identify, you have to select the lower I value. So for this question, the I value or which axis buckling will occur was not mentioned. Unlike the previous example, right? The previous example, it highlight what? On the previous example, it highlight that the buckling will not occur on the YY axis. It did tell you, okay? In this current example that we're doing, it's not. Okay, so the last section in buckling that you all should know, okay? I don't need this. I'm going to copy, okay. Again, these figures you all have, okay? Right. So we are going to design design of structural steel columns under centric. Okay, now we go back to centric, okay, not eccentric. Under centric loading, okay, based on allowable stress design. The thing to highlight is the allowable stress and structural steel. Okay, so if it's structural steel, okay, you will get a chart something looking like this. Okay, you will get a chart looking like this. Okay, so these are usually for structure, like for buildings. Okay, for buildings we tend to use structural steel. If we are designing, for example, we are designing a bicycle, for example, okay, a steel, then this chart is not valid anymore. Okay, so structural steels are usually used for buildings. Okay, and the condition and the criteria we are going to use, the design is based on what? Allowable stress design. Okay. Now, what is so critical? So as you can see over here, right? Again, this chart is very similar to what we have before. Only this one is under centric loading. Okay, this is under centric. So on the x-axis is L over R. On the y-axis is our critical stress. Okay, and then we have a value down here is 0.39 stress yield, and we have another value that is equal to 4.71 square root of Young's modulus divided by stress yield. Okay, so this is only suitable for structural steel. So if you look at any material handbook, okay, there will be a section on structural steel. Then you can use this graph over here. Okay. So what's so interesting about this graph over here? So I want us to focus between point A to point B. Okay, I want you all to look at point A to point B. Okay. So from point A to point B, the stress critical is equal to bracket 0.658. Okay, power of stress U over stress E. Don't worry, I'll tell you what stress E later on. And then this whole thing, close bracket, and we bring it down here, stress U. Okay, so I'm going to call this equation number 1. So this equation number 1 is an empirical equation. Okay, so i.e. someone did a lot of experimental work, okay, to get this, especially to get this coefficient. So if you were to plot on Excel this equation, okay, you will get a graph. You will get a graph, okay, that is valid from here to here, from A to B. Okay. So this above equation over here, so equation 1, okay. So equation number 1 is valid when LE over R or L over R is less than 4.71 square root of Young's modulus divided by stress U. Okay, so I'm going to define what the rest are, where sigma Y is your U strength. Okay, U strength, and sigma E is equal to pi squared E over L over R squared. Okay, and then this equation over here, all of you are very familiar. Okay, and then between now different limits. Okay, between point B to point C, right? Between B to point C, stress critical will be equal to 0.877 stress E. Okay, so it is only valid, or this is our equation 2. So equation number 2 is valid when L over R is greater than 4.71 square root of Young's modulus over stress U. Okay, so at point E, Okay, so now, sorry, at point B. So we're going to focus at point B now. Okay, so just now what we did is from point B to C. Okay, so we did from B